In this video, we're going to look at the amount of energy in an electromagnetic wave. We'll start by talking about energy density, and then finish by talking about average intensity and pressure exerted by electromagnetic waves. Recall that the energy density for an electric field is 1/2 of epsilon naught times the electric field squared. Also remember that the energy density for the magnetic field is 1/2 of the magnetic field squared divided by mu naught. So the total energy density would simply be the sum of the two. This is the simplest and most straightforward way to calculate the energy density of an electromagnetic wave. But recall that the speed of light is equal to the electric field divided by the magnetic field, and that the speed of light is 1 divided by the square root of epsilon naught over mu naught. If we solve for the magnetic field in the first equation and substitute it into the first, then we have a solution only in terms of the electric field. Further, we could use Maxwell's equation of the speed of light to eliminate that variable of the speed of light as well. When you do this, the result is that the energy density would simply equal epsilon naught times the electric field squared. We can do a similar process substituting the electric field into the equation, so we'd get the energy density in terms of just the magnetic field. That would get us that the energy density is equal to the magnetic field squared divided by mu naught. Or we could do a combination of the two, which gives us the square root of epsilon naught divided by mu naught times the electric field times the magnetic density. All three of these are very valid ways to calculate the energy density of an electromagnetic wave. All right, let's go through and let's actually find a better description now of energy density. Energy we talk about and density we talk about as some variable per volume. Well, what do we mean by energy density? We just saw that the electric field in an electromagnetic wave holds a certain amount of energy. And we've also seen that the magnetic field does as well. Since the wave is self-propagating, the energy within the wave is carried along with it. Perhaps the best example of this would be sitting on the beach absorbing sunlight. As you sit on the beach, sunlight hits you and you warm up. Why? Remember that temperature is just a function of energy, so the light from the sun, particularly ultraviolet light, is being absorbed by our skin, and the energy inside the electric and magnetic fields is then transferred into our skin. Now in this figure, you see a large gray box on the right side of the wave. The box has a width of delta x, which we can calculate as the speed of light times the change in time, which just comes from our definition of velocity. So in the next slide, when we talk about distance, we're going to write it as c times delta t. Also, the area of the box is just the area indicated here in the picture. And so the product of the two, area times delta x, would give us the volume. So the amount of the energy density that we've been calculating in the last couple slides is simply the amount of energy from the electromagnetic wave within this given volume that's shown by the gray box in this figure in a given amount of time. All right. So recall from the beginning of the semester that we talked about intensity. Intensity is another way to measure the energy of a wave. Specifically, the intensity is going to be the energy transported through a unit area, which we saw in the previous figure, per unit time. You can see this in this equation, where the intensity is equal to the change in energy divided by the area times the change in time. Now, if we multiply the top and the bottom by the speed of light, then the bottom gives us area times c times delta t, which, if you remember from the previous slide, is our delta x, or our distance. So area times distance just gives us volume. So energy divided by volume gives us energy density. So we find here then that the intensity of light is simply going to equal the speed of light times the energy density of light. We can use this in combination with our definition of energy density to come up with a simpler equation for the intensity of light based on the electric and magnetic fields. When we do that, we find that there are three ways to calculate the intensity. Epsilon naught times the speed of light squared times the electric field squared, epsilon naught times the speed of light times the electric field squared, or you could do the speed of light divided by mu naught times the magnetic field squared, and also the product of the electric and magnetic fields divided by mu naught. All three will give us the intensity of light, or conversely, if you have the intensity of light, you can get the value of the electric and magnetic fields. Since the intensity is proportional to the square of the electric and magnetic fields, the intensity will never be negative. So as the electric and magnetic fields oscillate, the intensity will simply oscillate between 0 and its maximum value. Knowing this, we can calculate the average intensity simply by taking the average of 0 and that maximum intensity. The average intensity would then become 1/2 of the same values that we found in the previous equation. Final topic that we need to discuss is radiation pressure. In addition to carrying energy, electromagnetic waves also have momentum. This is unusual since momentum requires mass and electromagnetic waves have no mass. As a result, many scientists often are heard saying that light is either a wave that behaves like a particle or it's a particle that behaves like a wave. We've already seen that the wave nature of light and the fact that it has momentum shows that it's a wave that behaves like a particle. We'll see in future chapters example of how light is better treated like a particle that behaves like a wave. In either case, since light has momentum, it will exert a pressure as it collides with other objects. We can calculate that pressure as either the average intensity divided by the speed of light if the wave is fully absorbed by the object that it hits, or if the wave is reflected, the change in momentum would be doubled, so the pressure would also be doubled, giving a pressure of 2 times the average intensity divided by the speed of light.